Hi everybody, and welcome back to part 8 of the Bravo project. Today we will be building our memory module. Our memory consists of two main parts, one being the RAM and the other one will be the flash memory. In this video we'll be focusing on our memory address register and our RAM, and in next video we're going to look at our flash memory. So with that, let's get started and have a look at the circuit, and then after that we're going to build and test it. All right, so let's have a look at the circuit for our memory module. As you can see, the circuit for our memory is a little bit bigger than the previous circuits that we have looked at. So what we're going to do, we're going to divide the circuit into two parts. In this video, we're going to go through part of the memory, and in next video, we're going to actually focus on the flash side. So let's first see what we have here. So in general, our memory modules have three sections. We have one section here at the top, which we could call it memory address register. And then we have our RAM chip, which is on the right-hand side of the screen here. And then eventually we have our flash memory along with a circuit that controls the bank that we are accessing actually on the flash memory. So we could say that we actually have three sections, right? In this video, we're going to focus on memory address register and our RAM. In the next video, we will be talking about the flash and the bank circuit and so on. All right, so with that, let's first see what is a memory address register. So as you may know, the memory address register is basically a register with some input which is connected to the bus and some output. And now the main responsibility of our memory address register is to address our memories. Basically, what is happening here is that we are going to read some data from the bus as an input to our register, and then we're going to output a specific address on our output lines. And those address lines are all directly connected to our memory. Now we have two types of memory here. One is our RAM, which is basically our random access memory. And this is basically our volatile memory, what we call it, right? So with this type of memory, if we remove the power from the chip, the data will be lost. However, we have another type of memory, which is more like a storage for our computer. And this is our flash memory, which is non-volatile memory, meaning that even if we turn off the computer, the data still will remain intact, and we could basically recall that data later. So these are the two types of memory that we have in our computer. And basically the memory address register circuit will be addressing both of these chips or both of these type of memories. And we're going to talk about that, how it actually happens. Now, let's first focus on our memory address register. So as I said, our memory address register is actually a 16-bit register, right? Meaning that we could address up to 64K of memory using this register. So the memory address register circuit here is very similar to our program counter circuit. If you have watched the program counter video, you know that we actually have 4 chips there that are all cascaded to each other, and these are basically 4-bit binary counters. I'm not going to go into details on this chip and how they operate. If you haven't watched the program counter video, I would recommend to watch that before actually continuing here. So what is happening here is that we have quantity 4 of 4-bit binary counters. These are 74 HC161s that are cascaded back to each other so that we have a 16-bit binary counter. So now you may ask why we actually have a memory address register here, why we have another 16-bit binary counter here, and basically why we couldn't just use our program counter output to address the memory. I guess if you're coming from a project like Ben Eater's 8-bit computer, that's probably a question here, because in that build we actually took the output of the program counter, and using that output we directly used it to address our memory. However, here we have a dedicated binary counter for our memory, for addressing our memory. And there is a reason for that. Essentially, having a dedicated memory address register here enables us to address memory whenever we need it, while the program counter stays at whatever step it should be. So as you may know, the program counter is actually responsible for pointing to a specific step in our program and fetch the next operation or next instruction from our memory to be executed by our computer. However, there will be a situation where we want to stay at the same step in our program counter. However, we want our memory to actually jump to a specific address while the program counter still stays on that specific step, meaning that the program counter and memory address register are not necessarily always synced to each other in regard to the step that is executed. Or maybe you could say that having a dedicated memory address register here enables us to have operations such as subroutines, and it is specifically important when we actually have stack operations. So let's say you have a program that has 5 steps, right? You run up to step 3, and in step 3 you want to actually jump to a different memory address and then do something there, let's say save a value, and then come back to the same step in our program counter. And that is achievable by having a dedicated memory address register here, which by itself is a counter, and it could actually count and basically move into different memory addresses and come back to the same address if needed. So that's why we kind of have exactly the same 16-bit binary counter here, but here we call it our memory address register. So with that, let's focus on our memory address register and see how it works. So as I mentioned, the memory address register have some inputs, and as you can see, just like our program counter, again, here we have a high byte and low byte concept, and the reason being is that our bus is actually an 8-bit bus. However, our memory address register is a 16-bit register. Therefore, if you want to have a 16-bit input into this circuit, we actually need to do it in 2 cycles, meaning that first we, let's say, read a value into the bus, and then we kind of read it into our register, into our low byte side of our register, and then we write a value to bus again, and we read that value into our high byte part of the circuit. And this way, using 2 cycles, we would be able to read the whole 16-bit that we need as an input to our memory address register. And that's why you see that the 2 chips on the right-hand side are connected to bus 0 to bus 7, and the same thing happening on the left-hand side. Again, the 2 chips on the left-hand side connected to bus 0 through bus 7. So the input side obviously requires a control logic so that we could go through that sequence of reading data from the bus for both sides. And again, if you remember from our program counter circuit, we actually had some signals we called them HI and inverted HI. And as you can see, we are using exactly the same signals here to control that sequence. So let's say that we want to actually read 2 8 bytes in 2, let's say, clock cycles into our memory address register. So what we're going to do, we're going to basically write the value onto our bus, And then what we're going to do, we're going to basically just bring the MI signal, which is memory in signal, high. So by default, when we turn on the computer, the HI signal is low and the inverted HI is high, right? So if we just bring the MI signal, or memory in signal, high, then as you can see, those two signals go to two inputs on a NAND gate, right? So if we have a high on both of those inputs, the outputs of this NAND gate will be low. And that's what we need actually to read the data from the bus into our register, because the parallel enable signal on these chips is an active low. So in order to read the data from the bus to these chips, we need to bring pin number 9 low, and that's what is happening here. So once we did that and we read the first 8-bit into our register, or let's say into our low byte side of our register, then we just bring the HI signal high, which causes the inverted HI to go low. And then now we have the HI high, the MI high, and then this basically goes to another gate in our NAND gates. And basically that brings the right line or the parallel enable line for the left side of the circuit to low. And that means that if we have a data on the bus, that data actually goes to our high byte of the circuit. So by definition, I guess probably from now on, we call the low byte side of our circuit the LSB, or least significant byte, and the high byte of our circuit, or high byte side of our circuit, call it MSB, or most significant byte. All right. So I guess this part is quite clear. It's going to happen in 2 cycles, and we're going to read a total of 16-bit into our bus. And that's basically happening when we actually want to set an initial value into our counter. So let's say we want to start from a specific memory address, and from there we want to count up. So we set that on the bus, we read it into our register, and now our register is ready to count from that address and kind of progress into next memory address and so on. So I guess that part is quite clear, right? And also we have another signal here, as you can see, called CEME. And this is basically, again, we use the same signal in our program counter. And basically this is count enable in our program counter circuit, and memory enable in here, because obviously this circuit is in our memory, but it's the same signal. And basically this signal goes to pin 7 and our counter chips, and what it does, it just enables counting. So as soon as this signal goes high, the whole circuit will start counting from whatever value that we have set through inputs. Now, so I guess the input side should be clear by now. Again, if it is not clear, I would highly recommend to watch the video on the program counter circuit, because I go into details of how this chip works and how this 16-bit binary counter actually works. Now, on the output side, there is a difference between here and what we had in our program counter circuit. In program counter circuit, we actually had 8-bit outputs. So again, even on the output side, we had a concept of MSB and LSB, and actually the output was happening into 2 clock cycles. However, here, since we need a total 16-bit output, because we will be addressing our memories, and those memories requires, let's say, 16 bits, then we're going to output everything at once in 1 clock. Therefore, on the output side, we actually do not need the HI or inverted HI signals. Essentially, what is happening here is that the whole output of the circuit, the 16-bit, will be outputted through 1 clock cycle, which is connected directly to our RAM and also our flash memory. I hope that it is clear so far. Now, let's focus on the address lines and how we could actually address our memory and output or input a specific value into our memory. So as I mentioned before, in this video we're gonna be talking about our RAM. So let me make this circuit a little bit bigger. So on the RAM side, it is actually a quite simple circuit, and the RAM here is exactly the same RAM as Ben Eder's 6502 project. If you have built that circuit, that RAM should be quite familiar to you. So the RAM has basically 15 address lines, right, from address 0 all the way to address 14. And if we want to point to a specific memory address, we just have to set that value on our address line. So it's basically a 15-bit binary number, and you just set that value on the address lines, and basically you're pointing to a specific memory address on the chip. The chip also has 8 output or input lines. As you can see, we call them I/O lines, which are connected directly to our bus. So through those I/O lines, we will be able to put the content of the memory onto the bus, or read something from the bus and save it into our chip. So let's see how it works. So other than the address lines, which are required to address the memory, and the bus lines, which are connected to bus, we really have 3 more signals. That's how simple is this RAM chip. And those 3 RAM signals, one of them is chip enable, which is basically just enabling the chip. This is like a master switch for the chip. If you want to enable the chip, you bring that line low, that's an active low line, and the chip will be enabled. And if you don't want the chip to be enabled, you just bring that line high. So that's chip enable, pin number 20. And we're going to talk about that in a minute, how we actually enable and disable this chip. And then we have 2 more lines, and one of them is output enable. And as its name says, basically it is put the content of the memory on the bus. And the other pin is a write enable, which basically put the content of the bus into our chip and save it to our chip. Now let's first focus on the write enable line, which means that when we actually want to write to our memory from the bus, we are going to bring that line, which is pin number 27 here, to low. That's an active low signal again. And as you can see here, we have actually a signal in order to do that, which is called RAM in signal. So let's see how that RAM in signal actually works. As you can see, the RAM in signal is coming to a NAND gate here along with our clock signal. So that means that we actually need to combine the clock and RAM in signals together through a NAND gate. And once both of those signals are high, then the output of our NAND gate will be low, and that's what we need because, again, as I said, this is an active low signal to write to the chip. However, if you have noticed, we have a capacitor here, and that capacitor basically enables us to have a specific timing for that RAM in signal to be high, meaning that these memory chips require a specific timing for the write operation, meaning that you could only have that signal high for a specific amount of time in order for the chip to do the write operation. And that's why here you see that the RAM signal actually comes to a capacitor, and whenever you bring that RAM in signal high for the duration of the time that the capacitor is charging here, the signal will be high, and then it's going to go low. And again, it's really all about timing and how long you want that signal to be high here. Again, using a 470 picofarad capacitor here, we are able to actually match the timing for our write operation here. And that's really all about it. So whenever we want to write something to the chip from our bus, we just bring the RAM in signal high, and essentially on the next valid clock cycle, the output of this NAND gate will be low, and the write operation is going to happen, and that value will be saved to our memory address or to our memory chip at that specific address. All right, so this is about the write operation. As you can see, the same signal is actually going to our flash memory. However, we're going to talk about the flash memory in next video. So let's now focus on the output enable, which is basically reading the RAM value and putting it on the bus. And that signal is quite simple. As you can see, again, this is an active low signal coming to pin number 22. And whenever we bring that line low, whatever is on that memory address will be put on the bus lines, right? So I guess that is quite simple. The only difference is that a RAM out signal is an active low signal. So we need to actually bring it low, and that will output the value onto the bus. Now, other than these two signals, we have a chip enable signal, which is connected to pin 20. And as you can see, this is actually coming from a little circuit on the left-hand side here. So now let's focus on that circuit, and that's going to be our last part for this video. Now, if you look at the output of our memory address register here, you'll notice that out of the 16 address lines that we have here, 15 of those are going directly to our chip, right, to our memory chip, meaning that we could actually address up to 32K of memory using this address line, right? Because if you have 2 to the power of 15, you would be able to address up to 32K of the memory, right? Now, the last line, or let's say the most significant bit in our memory address register output, which is the last pin here on the last chip, is actually a chip enable signal, meaning that we are not using that last bit for addressing here. We actually are using this signal as an enable or disable signal for our chips. So let's see how it happens. Basically, what we are trying to do here is that we want to have one of these chips be enabled at each point of time. And the reason being is that if you think about it, we have total of 16 bits here to play with, right? We actually have one of those pins which plays the role of enable disable. Therefore, we are only left with 15 pins or 15 bits here. And that 15 bits could only address up to 32K, whether it's on our RAM or on our flash memory. It doesn't matter. It only could address up to 32K, right? Now, our RAM is a 32K RAM, so we have no problem there. Everything is connected to our address line, and we basically could address all that 32K using our 15-bit output. However, we have also a flash memory here that we need to address, right? So how we could actually use the same memory address register to address both of these chips, and that's where a chip selector signal here comes into play. So that means that using this signal, we at each point of time, we either enable the RAM or enable our flash. So it means that at each point of time, you will be only reading and writing to one of these chips, not both. So let's say how it happens. By default, let's say that signal is low. Let's say that we just turn on the computer and the output of our memory address register is 0, meaning that all these output lines have a value of 0. At this point, because the most significant pin here is actually outputting 0, that means that, as you can see, this output is connected to the input of a NAND gate here. And the other input to that NAND gate, as you can see here, is connected directly to 5 volt. Now, at this point, just ignore that INH signal. I'm going to talk about that INH in next video, and it's actually not important. It's for expansion module or expanding the circuit in the future, and really has no role at this point. So let's ignore that signal. Just pay attention to the fact that this NAND gate here have one pin connected directly to 5 volt, so that means that it is actually always a high, and the other pin is actually coming from that signal from the most significant bit. So that means that when we actually turn on the computer, this signal will be low, right? So when this signal is low, the other one is actually high, connected to 5 volt through a resistor here. That means that our NAND gate is actually outputting 1, right? So the NAND gate will be outputting 0 only when both lines are high, right? So in this case, only one line is high and the other line is still low. So basically we're outputting high, and that means that we are not enabling our RAM. Our RAM at this point will be disabled. However, if you look at that same signal, that signal goes through a inverter here, through a 74HC04 chip, and therefore that signal will be high, right? And another pin here from another NAND gate is also connected to 5 volt, and since both of those inputs on the second NAND gate here are high by default when we turn on the computer, then the output of this NAND gate is actually will be low, and that means that we are actually enabling our flash memory. And by the way, the flash memory has exactly the same pin, which is pin number 22 as a chip enable, and basically that needs to be an active low. So by default, when we turn on the computer, we are pointing to address 00000, 16-bit of a 0, then we are actually enabling our flash memory. Now, as soon as we bring that line high, right, that operation will be reversed, meaning that now we have the two inputs on the first NAND gate going high, and therefore the output of NAND gate, the first NAND gate will be low, and then we actually are enabling our RAM. So, and at the same time, because again that signal will be inverted, we are actually disabling our flash memory. So you can see that this is like a on and off switch, and basically at each point of time you either make your RAM active or enable your RAM, or you make your flash enable, and the other chip will be basically disabled. So basically that means that if we have any address greater than 32,768, then we are bringing this the most significant bit high, and that means that we are actually addressing our RAM, or we are enabling our RAM. And that's why in this computer, when you change the address or your memory address register to 32,768, or in other words, when we change it to 8,000 in hex, then we are actually pointing to our RAM. If we are addressing anything below 32,768, then we are actually pointing to a memory address in our flash. So I hope that this part of enabling and disabling this chip is clear. It's basically just controlled through a most significant bit on our memory address register. So with that, I guess we are ready to go ahead and build the circuit, and then we're gonna go through some testing using our Arduino Mega Shield. All right, so we built our memory module. As you can see, I actually soldered everything, including the RAM and flash memory. However, as I mentioned in this video, we will be talking about the memory address register and our RAM. And in next video, we're gonna focus on the flash memory. So with that, let's mount this to our Arduino Mega Shield. And also I'm gonna add our LED board. So I guess it's ready for testing now. The only thing that remains is the power. And I'm gonna connect the power. And we should be good to go. Now let's have a look at the sketch first and go through different functions. And then we're going to come back to LED board and see what is happening here. All right, so I have loaded the sketch for testing our memory module. Now, I guess this sketch is quite similar to the previous sketches that we have looked at in the previous videos. However, something that I would like to mention here is that in the previous videos, we were using the bus lines. We are reading and writing to them. However, in this video, we start actually using the address lines. And as you can see, all the address lines in our memory address register are all mapped to a specific pin in our Arduino Mega Shield. And that's why we have this array here, basically just defining the pins that are connected to our address line. Now, to be clear here, these are actually the output of our memory address register, the address lines from, let's say, 0 to 15. Now, the rest of the functions here should be clear. We have talked about those in the previous videos. It is basically just some functions to initialize our Arduino Mega Shield and set all the pins and signals to a default value. So the main functions are going to start from here and here. Again, we have two variables, one a delay, so that we could create a delay in between the control signals so that we could see the LEDs, and the other one is just our clock length. So the main functions for testing our memory module starts here in our setup function, and the first function is a reset mar. Now, if you have noticed from this circuit, you see that we actually have all the master reset lines connected to 5V permanently. And that means that we never actually want to reset this circuit using a signal. The master reset line is an active low signal, and if we wanted to reset the circuit using a signal, we should basically bring that line low. And this is actually what we do in our program counter circuit, if you remember. However, for the memory address register, there is no need for that, and essentially that's why all the lines here, or the master reset lines, are connected to 5V. So essentially in this computer, we never are gonna reset our memory address register using a signal. I mean, there is no need for it. If you want to change a value, we just write the value to the bus and kind of write that value into our memory address register. However, here in this test functions, because I'm running those functions back to back, at some point I would probably need to reset the memory address register to 0, and that's why we have that simple function here. And if you look at it, it's quite simple. What I'm doing here is really I am just setting the bus lines to output, because we are going to write something to them, and then I'm going to write value of 0 to the bus. And again, these functions are the ones that we actually talked about those in the previous videos. So you could basically look at those functions and see what is happening if you're not familiar with them. So we're writing a value of 0 to the bus, and then I'm just bringing the MI, or memory in signal high, and I'm going to write that value into our memory address register by pulsing the clock. I'm going to repeat the same process. However, here I'm actually bringing the HI signal also high. So this is again writing a value to the LSB, or least significant byte, and our MSB, which is most significant byte. So essentially a value goes on the bus, and we're going to basically read it into the LSB part, and then we're gonna read the same value into our MSB part. So that's all it does. And since the value is 0, we're kind of resetting everything back to 0. And at the end of the function, I'm just gonna set all the bus pins to input, because maybe we want to actually read something from them. So I guess this part is quite clear. Now, after resetting our MAR, we have a couple of functions. The first one is what we call it set MAR, or set memory address register. And what this function does is basically it initializes the memory address register with a value, right? So let's have a look at this function and see how it does it. So set MAR is, again, setting the bus pins to an output, and then it accepts a parameter, right? We are passing a parameter to this function. What it does, it divides that value, which is an integer, and basically it divided it to 256, and that's going to give us our high byte, right? And then if we repeat the same process and divide that value by 256, but only get the remainder of the operation, then that's going to give us a low byte. Again, I guess I've talked about this method and this function in details in our program counter circuit or sketch in the past, so I'm not gonna repeat everything here. But again, we get the low byte, we get the high bytes, and we're gonna go through, you know, bus lines one by one, and basically write those values to bus lines, and eventually we're gonna read that value into our memory address register. So as you can see, for the first step, I'm setting the MI signal high, and that's a memory in signal, right? So this is the memory signal in, and we're going to combine those with HI and converted HI in 2 cycles. First, we're going to write into our LSB, and then we're going to write the same value, or basically the other value, which is for the most significant byte, into our MSB. So that is what is really happening here. The HI signal initially is low, the inverted HI is high, and the memory in is high. We pause the clock, we read that low byte into LSB. We're gonna repeat the same process here, except that this time we're gonna basically make the HI high and the inverted HI low, pause the clock, and read the value into MSB. Now, the last part is just setting all the bus pins into input again. So I hope that the set MAR part is clear. I guess, again, this is very similar to what we did in our program counter circuit. Now, let's test this and see what will happen. So let's just set the MAR to a simple value of 1. I'm gonna test the sketch, and I'm gonna let's actually increase these timers to 1 second, just to be able to see the LEDs. All right, so as you can see on the LED boards, we are actually setting a value of 1 into our memory address register. And remember, these LEDs are actually connected to our address line from address 0 all the way to address 15, and that's it. So let's test another number. Maybe this time we do 255, just to see if our setMar function is working properly. And as you can see now, we have a value of 255 in our memory address register output. I guess this part is clear. Now we could move on to next function, which is stepMar. So stepMar is a function that basically steps our memory address register. Again, our memory address register is just a counter, so we could actually set a value, and then we could start counting from that value forward. So what we could do here, we could, let's say, set our MAR to 0, and then count, let's say, for 16 steps from 0. So first, let's have a look at the stepMar. And stepMar, as you can see here, is quite simple. The only thing here is that we are bringing the CEME line high. And if you remember from the circuit, this signal is actually connected to the count enable pin in our 4-bit binary counters. So by bringing this line high and then just pulsing the clock, this whole counter circuit will start counting, starting from the chip on the left hand side and moving on to the next chip and so on. So basically we are just pulsing the clock, the counting will start, and then we're going to see the outputs of those counting in our address lines. So let's do that. And here there's nothing really special other than the fact that we have a for loop. We get that number of steps that we are passing to the function, and we are going to basically go through those steps one by one. We're going to do a digital read on address lines. So essentially when we are pulsing the clock and counting, we're going to read the output of the memory address register, and we're going to print them in different formats, binary, and then hex, and then decimal on the screen. So I guess that's quite clear. And eventually we're going to just set the CME signal back to low. Now let's go ahead and actually execute that and see what will happen. So initially I'm going to set the MAR to 0, and then I'm going to step the MAR for 16 steps. All right. So let's check that and upload the sketch. All right, so as you can see, we are actually starting from 0, and we are counting one by one, and we are reading actually the output of our memory address register. Again, this part is the binary value. The next part is actually the hex equivalent of that, and finally we are printing the decimal equivalent of that on the screen. All right, so I guess this part is clear. So now what we could do, we could actually reduce this number. So let's say to a smaller number, 10 milliseconds, and maybe we could just increase that number for testing, and then we could we could do another thing. We could actually start from a different value here so that we could test that as well when we are counting. So let's start from 512. So we are going to initially set our memory address register to 512, and then we're going to step MAR for another 512. So essentially we should end up with address 1024 if everything works properly, right? All right, so remember this is the number of steps that we're actually counting from whatever value is on the MAR. Therefore, if we start from 512 and move on for 512 steps, we should end up with 1024. All right, so let me check that and clear the screen, and let's run the sketch. All right, awesome. So as you can see, we actually this time are starting from 512 as our initial value, and then we are counting all the way to 1024. All right, so I guess this is quite clear. Now, we could change these values to any other value and basically test it up to 64,000. Obviously, we could output 64K in our memory address register. But I leave that to you. So if you want to basically test that, you could set that number here and let it run for a while, and you're going to see that actually every address is printed on the screen. Now, the next step would be to basically step our memory address register, and at the same time you want to actually read the content of our RAM, right? So in order to do that, I wrote a separate function here, which is quite similar to step MAR, except that it not only steps our memory address register, but it also reads the content of the memory and print it on the screen. So with that, let me just comment that out, and we're going to have a look at the step MAR and read of RAM. Now, going back to the circuit, if you look at it, what is happening here is that we are actually outputting those values on our address lines. Those address lines are connected to our memory. Therefore, we are actually addressing our memory. And the only thing that we need if we want really to see the content of the memory on our bus line is just to bring the RAM out line low. and that's it. That's going to basically put the content of that specific memory address onto bus, and then we could read it through our bus lines and print it on the screen. So this is actually what is happening here. Let's have a look at the function stepmar read RAM. Again, stepmar read RAM, the first part is quite similar to what we saw in the stepmar. We're just, get a value here and we have a for loop. The only difference is that here, when we are actually reading the address line, right after that we have a short delay here, and then we're gonna read the memory lines as well. So as you can see, we are bringing the RAM out signal low. This is an active low signal. Therefore, at this point, the content of that memory cell will be on our bus. And as you can see, we're just reading that bus value. And again, read bus is a function. This is one of those that we talked about it in previous videos. It is basically a function that goes through our bus lines one by one and read the value of those bus lines, kind of compile them into a single variable, and it's going to return that variable to return that value to us. So here, setmar and read RAM, it just calls that function so that we could read the bus line, and whatever we read on the bus at this point is actually the value that is outputted by our RAM, right? And then finally, what we're doing here is again repeat the same process, reading the address lines and printing everything on the screen. So at the first section, I'm printing just the address line, just like what we did here. And then I have just a little text here that points to the data. And in the basically second part of the output, I'm printing actually the data, which is our memory data that we are getting from our bus. All right, and eventually I'm gonna just set the CME low again and putting that signal to default. Okay, so let's have a look at that now. What we're gonna do, the only thing that is important here is that because we are actually printing the content of the RAM here, we want to make sure that we set the value of the memory address register to the first address of the RAM. So what I mean by that, if you remember when we talked about the circuit, we said that if we actually set the value of our memory address register to any number equal or greater than 32,768, that would actually enable our RAM, and basically we'll be pointing to actually address 0 in our RAM, right? So if you think about it, 32,768 will enable the RAM. However, since all the other lines are 0, we are actually pointing to address 0 of our RAM, right? So that's why here, if you really want to read our first address in our RAM, we first need to set the memory address register to 32,768, okay? And then from that point, we're gonna step the mar, go to address 1 of the RAM, address 2, and so on. We're gonna basically step our memory address register by 32 steps here, let's say, and then print the content on the screen. So let me clean the screen and just run this function and see what will happen. All right, so as you can see, we resetted the mar. We actually set the first address to 32,768, which is equivalent to 8,000 in hex. And as you can see here, the most significant bit is actually high, and the rest of the outputs are 0, which basically means we are actually pointing to the first address in our RAM, right? And then at this address, as you can see, I'm reading a random value, and this is basically the hex equivalent, and this is the decimal value. So as you can see, as you may know, RAMs are actually it's a volatile memory, so when you turn it off and you turn it on again, you're gonna basically get junk in the RAM. You could get any value in any cell, so It is completely normal, and as you can see, we actually are reading different values in different memory addresses. All right. So I guess that's about reading the RAM. Now the only thing that remains here is really to go ahead and write to the RAM, right? So we were able to read from RAM, and now let's have a look at this function that is actually writing to our RAM. Now what we could do here is we could write another sketch here that actually populates our RAM. And in order to do that, the only thing that really we need is just set something in the bus and then bring this write enable signal low. And this way we're going to actually save that value into our memory. And that is what is happening in this function here. Okay, so let's have a look at the populate RAM function, and this function accepts 3 parameters. The first parameter is basically the first address on the RAM. Whatever address you want to set it, it will start with this address. The next one is a number of steps that it will take from that memory address. So basically you could set any number here that is less than 32,768 because this is the maximum number of memory cells that we could have. And then the last value is just the value that we want to populate the RAM with. All these cells, let's say from memory address 0 all the way to memory address 16 here, will be populated with this specific value. So you saw on the screen that we actually had garbage right in our memory. So now let's run this and actually see what will happen. Before that, let's have a look at the populate RAM function here. And as you can see, I'm just printing some comments here on the screen. But what I'm going to do here is that I'm going to actually define some variables here. The first one is that the first memory address. And as you can see, I'm actually adding 32,768. And basically that's an offset, right? So let's say we want to start from memory address 0. Memory address 0 is actually memory address 32,768 from the memory address register perspective, right? So this is just offsetting that memory address so that we are pointing to the right memory address in our RAM. And then the last memory address obviously will be our first memory address plus number of steps that we want to move forward. And really that's all about it. Then I have a for loop function that goes through the values one by one. And what it does, it basically, as you can see, set mar. So we talked about this function at the top, right? Set mar to that value. So let's say the first value is actually 0 plus 32,768. So it sets the mar to that value and then set the bus pins to output and then write to the bus that value, because now we're actually going to write something to the bus or eventually to our memory, right? So write that value to the bus, and then as you can see, I'm bringing in the RAM in signal high, right? So this is the signal that we need to bring in high, and with the next clock pulse, which are happening here, that value will be written to our RAM. And eventually we're going to just set that RAM in signal back to low, right? So I'm going to basically write those values to all the addresses in that range. That's really what is happening here. And finally, I'm going to set the bus pins to output and again set my memory address register to the first address. And we are basically here preparing for the next step, which is actually reading the memory, right? So let's say we started from address 0, we moved to address 16. At this point, we are actually pointing to address 16. So using this line here, I'm just going back to address 0 because we will be reading the lines. And really that's all about it. So let's test it and see what will happen. So I'm actually gonna, because that is gonna happen automatically in the function. So what I'm gonna do is just I'm gonna populate the RAM, and then I'm going to step the mar and read the RAM. Okay, so let's populate, let's start from address 0 of the RAM and move on for 16 and populate all of those with 255 decimal, which is going to be FF hexadecimal. All right, so let's just clear the screen and run this function, see what will happen. All right, so you see that that writing happened immediately, and now you can see that from actually address 0 all the way up to address 16 in our RAM, we are actually getting FFF in the output, or FF. So yeah, that means that we're actually writing to our RAM, and our write operation is working properly. However, as you can see from address 17 to the last address, we are actually still reading junk because obviously we didn't write anything to those addresses. All right, so I think everything here is quite clear, hopefully. So you could obviously play with these numbers, you can change those values. However, the important thing here is that if we actually want to work on our RAM, you want to make sure that we are setting that mar to 32,768, and that means we're pointing to the first address in our RAM chip. I commented that out here because inside that function inside this function I'm actually doing the same thing as you saw below in the function. All right, so I guess that's it. I hope that you guys got an idea about how to test our memory and different functions that we have here. Obviously, you could be creative and change those numbers, or even change the functions and come up with your own way of testing the memory. All right, so with that, we're going to conclude this video, and in the next video, we will be talking about our flash memory. All right, see you there.